In 1994, the Northridge earthquake struck the greater Los Angeles area in California. The shaking was so intense in the West San Fernando Valley that buildings collapsed and bridges were ruined. Billions of dollars of damages were inflicted on parking garages, office towers, apartments, and warehouses. Thousands were injured and 57 people died. One factor that compounded the earthquake's devastation was the extent of the damage it caused to hospitals. Just when they were needed most, 11 of the area's hospitals were completely or partially closed, with patients evacuated to outside medical centers. But one hospital stayed open. At USC University Hospital, now USC Keck, patients felt the rumble, but it was more of a gentle sway than the violent tremors felt in other parts of Los Angeles. The facility was one of the few in the area that was able to accept new patients after the earthquake. The reason it could stay open amid the chaos all comes down to the foundation. The hospital was built in 1991, only 3 years prior to the quake, and the design included what was a pretty innovative idea for its time, at least in the US. It's dead simple in theory, just physically decouple the superstructure from the ground. Of course, in practice, there are a lot of engineering details to get right, so I built a little model to show you how this works. I'm Grady, and this is Practical Engineering. Earthquakes can put enormous demands on buildings. In seismically active areas for low and mid-rise buildings, there really is no worse loading condition for structural engineers. It's a big deal. Earthquakes are a lot like floods. You can't predict the timing, and their intensity varies tremendously. In most situations, you just can't afford to design for the worst case. If you can imagine a destructive earthquake, there's an even stronger one possible. Of course, they're difficult to design against, and we'll get to that, but there's the additional challenge of just drawing a line in the sand that says, this is the level of risk we're willing to accept. With floods, we often choose a somewhat arbitrary limit, like the 1% storm, to size drainage infrastructure and delineate the floodplain where development is restricted. Same idea with earthquakes. The code outlines site-specific seismic risks across the US and says essentially, your building has to survive this amount of shaking. But that word survive might not mean what you expect. Earthquake accelerations and the resulting deflections can be so strong that it usually isn't feasible to design a building to completely resist the forces. Instead, we design buildings to absorb earthquake energy by deforming and yielding in a controlled and predictable manner. Seismic loads aren't like other structural demands, like gravity and wind, where we add strength as needed to resist them entirely. If the design earthquake required by the code ever comes, the expectation is that ordinary buildings are going to be damaged, maybe even beyond repair. The intent is simply that they don't collapse. Let's go to the garage and I'll show you what I mean. I designed this little shake table so we can simulate an earthquake on the bench. It just uses a cordless drill for motion. I'm doing this in one dimension for simplicity, but most earthquake engineering has to consider shaking in any horizontal direction. Vertical motions aren't usually as intense in earthquakes, and buildings are a lot stiffer in the vertical direction since they sustain a full G of vertical acceleration constantly, so it's not as big a factor in design. I built a little building using these magnetic pieces, and let's give it a little shake. This is exaggerated for effect, but I wouldn't want to be in there. It's a little worse for wear after the quake, but as a whole, it's still standing. This is what the code allows for many types of buildings. It's all about life safety, protect the people inside. And it's generally a reasonable trade-off. For rare events like earthquakes, it's often just not feasible to invest in a building that's strong enough to come away from the shaking unscathed. But there are situations where it makes sense to have additional protection. Hospitals are the perfect example. Even if the building doesn't collapse, it might need to be evacuated and closed while the structure is repaired after an earthquake. Lives are still endangered by interruptions in procedures and lack of capacity. And think about all the expensive equipment and contents inside. Even if the building itself survives a major earthquake, a lot of that stuff is going to be damaged beyond repair. When you factor in the impact of ruined contents and the time it would take to get things back up and running, it tilts the calculus of savings versus safety when it comes to earthquake design. This concept is called resilience. For offices and homes, we might be willing to accept the risk of having to rebuild after an earthquake to avoid the cost of building an extremely strong structure. For hospitals, fire stations, emergency shelters, and other critical buildings, it's just not acceptable. They need to be more resilient. But there's a challenge there. Let me stiffen up my building on the shake table and I'll show you what I mean. Now this structure is resilient against earthquakes. Give it a good shake and all the pieces are still connected just the way they were before, but watch what happens when I put some stuff inside. Almost all the accelerations from the ground are transmitted through the building, where contents feel the shaking. You can see how stiffness plays two parts. It keeps the structural members from bending and deflecting so much, but it also means that more of the accelerations are felt by the building and what's inside. So sometimes we need an alternative. For that, we need to look at an earthquake. This is an accelerogram of an earthquake. It's a simple plot to understand: time on the x-axis, acceleration on the y-axis. It looks almost like a sound wave you might record through a microphone. By itself, it isn't that useful at first glance, except, I guess, to let you know that earthquakes are noisy. The ground movements are broadband. They contain a lot of different frequencies, and frequency matters a lot in seismic engineering. Let's go back to the garage to see why. I have a few rods set up on the table now. These are very simple oscillators, and I can excite them with my drill. If I shake it slowly, the longest rod has an extreme response while the others are mostly unbothered. A little faster, and now it's the medium rod responding. Faster still, and the smallest rod is responding while the other two are barely moving. The displacement is the same for all three oscillators, but the response is completely frequency dependent.
This is so silly.
I think this is pretty intuitive. Instead of frequency, we usually talk in terms of period in seismic engineering. That's the time it takes to complete one cycle of an oscillation. Every structure has a fundamental period at which it naturally sways. For short buildings, it's usually less than a second. For skyscrapers, it can be multiple seconds. And the closer an excitation gets to a building's fundamental period, the more its response to that excitation grows. Imagine if I could build a shake table with a lot of these oscillators ranging in fundamental period, and then take our accelerogram from earlier and feed it into the demo. Some of the oscillators would shake a lot, some barely at all. If we plot the response of the whole group, we get this graph called a response spectrum. This is the plot for a single event. For many earthquakes, acceleration tends to peak for periods less than a second. Plus, oscillators with a longer period naturally smooth out rapid ground motion. So it's pretty typical that you have a stronger response at the lower periods. The building codes look at a wide range of earthquakes to create site-specific hazard curves that look a little like this: a high plateau at the shorter periods that decays as periods get longer. If you're the designer of a low or mid-rise building, this curve is an issue for you. With a shorter fundamental period, your building is at the worst part of this curve. It's the most susceptible to seismic ground movement. This is why it's common to see more damage in shorter buildings after an earthquake, when the skyscrapers survive unscathed. Lower buildings have shorter fundamental periods, so they have to be designed against much higher accelerations. But what if you could just adjust a building's natural period so it feels less power from the earthquake? That's the idea with base isolation. Let me set up another example. Now my building is on rollers and I'm using rubber bands to hold it in place. I'll put the two examples side by side so you can see the difference. Pretty remarkable. And here's what happens to the stuff inside. What I love about this solution is how intuitive it is. You know, all that exposition about acceleration spectra and oscillators and ground motion response, you don't need any of that to understand how this works. And because of that, it's not really a new idea. The concept of using a loose connection between foundation and underlying soil has been used for centuries, and many historic monuments and buildings have probably benefited from an isolated base, whether it was an intentional seismic protection or not. Lots of older patents on the idea make use of rollers or ball bearings, kind of like my demo. The general idea is the same in all cases: make the structure's fundamental period longer to get the peak accelerations down. Modern designs typically use one of two solutions. The first is rubber bearings. Instead of resting directly on the pile foundation, isolation devices separate the superstructure from the substructure. When an earthquake comes, the building acts more like a skyscraper, smoothing out the high-frequency ground motions so the floors feel less shaking. Early isolators were plain rubber, but it didn't work that well. It would bulge out under the weight of the building, making the bearings less effective over time. Modern isolation bearings use a composite of steel plates with rubber in between them. This makes them highly elastic in the horizontal direction, but stiff in the axial direction, so they can withstand a lot more load without bulging. And this system has a lot of advantages. Of course, you get the lengthening of the building's fundamental period, which lowers its response to most earthquakes. That makes a huge difference in resilience for both the structure and the stuff inside it, shortening or entirely eliminating the time required to put it back into service after a seismic event. It also means the structural members themselves don't have to be as strong. I put the original, more flexible structure on the shake table with the isolation system, and it held up just fine. Even the stuff inside was mostly unbothered by the shaking. So you sometimes see an offset in the cost of the isolation system from the rest of the building. And there are situations where they pay for themselves entirely. They're also big for retrofits. Strengthening older buildings to meet modern seismic codes is often disruptive to architectural elements or even to the structure's function. New beams and braces require removal of decorative features or changing the floor plan. Instead, you can just temporarily support the building and insert isolators below. That's exactly what they're doing on the Salt Lake Temple in Utah, and the same idea has been used in a lot of seismic retrofit projects across the world. That's a lot of advantages, but we can do even better. Isolation lengthens the fundamental period, reducing the building's response to an earthquake, but it doesn't inherently absorb the energy. We don't want our buildings to vibrate like a guitar string ringing out, so damping is also important. There are lots of ways to improve the damping of buildings. I've done a couple of videos on unique solutions in tall buildings. But base isolation systems make it easy. You could just use a special blend of rubber in the bearings that absorbs some of the energy instead of transmitting it into the superstructure, so-called high damping rubber. Another option is to use a lead plug in the center of the bearing. As the plug plastically deforms, it absorbs the energy of the shaking. This reduces the accelerations of the building even further and helps kill the oscillations faster after an earthquake, so the building doesn't ring like a bell. And not just buildings, but other structures too. Lots of bridges use similar isolation systems to manage earthquake loads. Rubber bearings are a great solution and probably the most widely used base isolation system, but their properties can change based on temperature. They're kind of bulky, they're susceptible to damage from exposure to oils and ozone, and they can degrade with age. They're not always the perfect fit for every application. An alternative is curved surface sliding bearings, often known by one of the most common trademark names, friction pendulum isolators. Instead of rubber, these use a sliding element on a curved surface to separate the superstructure and substructure. If an earthquake comes, the building rides on the bearings. Damping comes from the sliding friction, and the restoring force comes from the curved surface, keeping the building in place when the shaking is over. These get pretty creative with 2 or 3 separate elements that offer more control over the displacement and period under a wide range of accelerations. The amount of displacement a building experiences on isolators is pretty important because buildings don't just float on their foundations, they're connected to stuff. People have to get in and out of buildings, of course. Usually that's not so complicated since most structures don't move relative to the ground, but it's not true for base isolated buildings. For the system to work, a building's only connection to the ground has to be through the bearings. So buildings equipped with a seismic isolation system often have some kind of moat around them, providing a space to move. It's usually pretty easy to spot an isolated building because it has a big gap all the way around, although often this joint is bridged with some kind of expandable cover, similar to the way expansion joints work on bridges. Utilities are also a challenge. You can't have a solid water or sewer connection to a building that wiggles around. So engineers have to design sometimes elaborate, flexible connections for water, sewer, gas, and electricity. Finally, you have to be thoughtful about long-period earthquakes. There are situations where a base isolation can actually amplify the shaking if it's not carefully tuned. Earthquakes are such a challenge in engineering, unpredictable both in time and intensity. There's only so much you can do when the ground underneath your structure shakes uncontrollably. But I love this solution of base isolation because it's so intuitive. It's something my 5-year-old would come up with. Just put a suspension system on a building. But it works. It works really well, actually, to the point where it's been installed on thousands of buildings across the world. It's not a catch-all, but I suspect that as the technology improves, and as we get more data about how these buildings perform in real-world situations, it's only going to be more common to see little moats around important buildings in seismically active regions. Most people will probably never notice, but you and I will know what's underneath. I love talking about the engineering of the built world that often goes unseen, like the isolation bearings below lots of famous buildings. It can be hard to appreciate how this stuff works, so a lot of my videos feature these demonstrations I build in my garage, and a lot of those models feature parts from today's sponsor, SendCutSend. Honestly, the fact that this is possible, let alone affordable, is incredible to me. Design your part in your favorite CAD software, upload it to the platform, choose any additional services like bending, tumbling, countersinking, or tapping, and get an instant quote. I love the price transparency, and I even go back to the drawing board sometimes to make revisions and try and get that cost down. Parts are made in the USA, they're out the door in a day or two, and there's no minimum quantity, so the value proposition is hard to beat here. I could spend half a day in the shop making a part, or I could have SendCutSend do it for me for a very reasonable price, freeing up my time for other stuff. It's just unlocked this whole new world of possibilities for the stuff I build. If you're in the US or Canada and want to give it a try, click that link below for a discount on your first order. Thank you for watching, and let me know what you think.